Okay, a very good morning, everyone, and welcome to another HSMA training day, or half day, as it is today. So today is going to be the kind of final one of the sort of October series, which has been all about providing you with the kind of fundamentals for the kind of tools that you're going to be using and the approaches that you're going to be using. So obviously most of it talking about how to code in Python, but also we had a bit about sort of model design and conceptual modeling. And then we've also had this module, this sort of mini module, module 2, where in the first session we showed you the various integrated developer environments that you're using, things like Spider and Colab and Jupyter Lab. And then in this session, which is the second of the module 2 sessions, we're going to be talking about what it means to develop in a free and open source way, which is very important. The entire HSMA program is built around the philosophy of developing in free and open source. And also taking you through version control, which is a really important good habit to get into, especially if you're sort of new in your coding journeys. Very good to get into the habit of doing version control, good solid version control right from the off, and particularly important as you come onto your project work in phase 2. So after this week, basically all of the training from next week onwards is going to be focused on showing you all the fun things that you can do with these new skills we've shown you. So how using Python and all of your collaborative development skills in order to be able to build discrete event models, or build a machine learning algorithm, or a natural language processing algorithm, or a geographic model, or whatever it may be. So from next week onwards, we'll be looking at that. So this is the last of the kind of foundation stuff to give you the kind of tools and techniques you need. Just before I sort of carry on, I'd like to extend particular thanks for this first half of the session to my colleague Mike Allen, who provided a lot of content. He's a big advocate of free and open source software, and has delivered numerous talks about the benefits of free and open source, and why in the scientific community in particular this is really a really important approach. So thanks to Mike for allowing me to nick a lot of his ideas in a very free and open source way, and as you'll see in the second half, I've nicked a lot of my colleague Tom's stuff. So this entire session is very much free and open source in that I've nicked it from other people. So what is free and open source software? Free and open source software specifically refers to software that can be used and changed by anyone for whatever purpose they need, and that's the free bit. It's very often confused with free as in it doesn't cost anything. It usually doesn't, although there's nothing stopping you charging for free and open source software. There's absolutely no limitation on that, and in fact some companies do. Anybody that's aware of some of the Linux operating systems will be aware that some of them you buy. Not many, but there are options out there. So that's the free bit, that anybody can basically use and change that piece of software. And the open source bit is that it can be interrogated by anyone to see how it works. In other words, you can look under the bonnet and see how this particular piece of software is working. You can look at the code and understand it. And free and open source software is kind of the opposite of proprietary software, which is most of the software that you, and indeed all of us, are used to using, where you have software that's distributed under copyright licensing, and the source code is typically hidden. So, if you boot up your copy of Microsoft Word, you can't go in and see how they've coded Microsoft Word underneath. And as I say, it is possible to have open source software that you can charge for, and it's also possible to have open source software that is not free in the other sense as well. So you can have open source software where you can see, and it can be interrogated. The code can be interrogated by anyone, but it can't be changed. So I'm going to talk a little bit this morning about first about the history of free and open source, and where this has come from and how it's evolved, and then talk about why I think this is important, particularly for the kinds of things that you guys are going to be doing and the kind of work that you will be doing as data scientists and indeed analysts. And there's very often a misconception that free and open source FOSS is a pretty new thing, but actually that's not the case. It's not a new idea, and I think a lot of this comes from the fact that proprietary software has been so dominant over the first few decades, in particular of the home computer boom. So moving from the sort of late 70s and early 80s, moving forward, particularly, I think there's been a lot of focus on dominance from proprietary software. And of course, you'll all be familiar with probably one of the biggest software companies that we all have software for. Mentioning no names here, the big M. And of course, there is a definite dominance from that particular company in terms of the operating system, which is still the most widely used operating system in the world. And so this idea that free and open source is a sort of new thing and is a bit different and it's a bit odd, and it's actually not true. There is a lot of history to free and open source, and in fact, just to prove that point, I put to you that the first non-trivial computer program was developed in 1843 by Ada Lovelace for Charles Babbage's analytical engine, and it was open and shared. So there you go, the first proper computer program that would resemble something, albeit in a very different form, that we would later, over 150 years later, come to sort of recognise as a computer program, was open and shared freely. There was no sort of concept that this was hidden or proprietary in any way. So in the very early days of computing, software was very often bundled with hardware. So you would typically, it would be less often people, because in the early days, not so many people had home computers. That was very rare. It was usually businesses, and later sort of very nerdy hobbyists that were very into this new thing, who were essentially buying computers, but they essentially bought the computers almost because of the software that was installed on it. So it came with the software they needed. So if it had some sort of word processing software that was bundled in and installed in that computer, then that's part of the reason they bought it, because the computer and the software were kind of seen as synonymous. They came together. But in the late 60s, early 70s, there was a new software market that started to emerge, and software was increasingly being seen as something separate, something that could stand on its own 2 feet, and something that you could create software and you didn't have to automatically accept the software that came with the computer, and that you could have other software that you could bring in. But of course, if you start going along that line and you're developing software, these new software packages, and you're selling that separate to a computer, because you're not, it's not coming bundled with the computer, there needs to be some way in which you need to make money, and so people started to charge. And infamously, Bill Gates in 1977 wrote a letter to he was one of those early hobbyists, and wrote a very angry letter in 1977 in a hobbyist magazine, basically saying, why on earth is it fair that people who are developing, those of us who are developing software, aren't getting paid? This seems wrong, and that we need to put some value on software, and that people should consider software in the same way that they consider hardware. But this particularly great line, I would appreciate letters from anyone who wants to pay up. And of course, infamously, you may have heard the story of when Bill Gates first approached Alan Sugar many years ago with the idea of selling software, and Alan Sugar thought he was completely mad. at the time. And that kind of goes back to this idea that you have to imagine it was very difficult to conceive that something that you couldn't, was sort of more abstract and wasn't a physical thing that you could hold in your hands, but rather some data on a computer that you could charge for that. But Bill and others were very keen on this idea that we should be charging. They're putting in work to build it, to maintain it, to find all the bugs and the errors, etc., and that they should get remunerated for it. So in the 70s and 80s, as this sort of idea began to take hold that maybe you should be charging for software companies began hiding the code. And we had the emergence of closed source software, so that you would have a piece of software where you couldn't see how it was built, because actually we're starting to charge for it now. We don't want you to see how it was built, because maybe that now you'll build something that's even better based on what we did. And then crucially in 1980, the copyright law in the US was extended to cover software. And up to that point, software was not considered copyrightable. Because they were thought to be ideas or methods or processes, and that's not something you can copyright. And again, it goes back to this idea that people really struggled with this concept of being able to see software as something that was a tangible thing for which you could charge money. And of course, from that point onwards, we've had a largely proprietary software dominated history. And so I put this up to sort of, the various journeys for those of us old enough. Some of these particular journeys may look more familiar than others. We've got the sort of the Microsoft journey going through from MS-DOS through to the emergence of Windows and Windows 95, and of course Windows still going strong and dominant now to this day. Apple, to a lesser extent, obviously found a good market in more modern day, but certainly at the start they were very, very niche and struggled for a long time to get a real solid foothold against the dominance of Microsoft. And then, of course, all of these sort of 8 and 16-bit computers that emerged in the 80s and 90s, that all just fell away. I mean, the dominance of Microsoft in particular just killed a lot of these things off, and we had the big companies of Commodore and Atari, big names in home computing, and obviously Sinclair in this country with the Spectrum, which was certainly dominant in this country for much of the 80s. Commodore in particular, I would still argue this thing here, the Commodore Amiga, greatest computer ever made. That's a statement of fact. So far ahead of its time. There were some wonderful things that came out. The Atari ST with the greenest operating system, quite literally in the world. Fantastic computers that emerged with some really forward-thinking ideas, but they all eventually crumbled. They all eventually disappeared, and we had this large dominance from Microsoft to the extent where pretty much from the sort of mid-90s onwards, if you owned a computer, you had Windows installed, and it was as simple as that. And maybe you had a Mac if you were one of those trendy types and didn't want to wanted to buck the trend. And then, of course, it wasn't long before offices across the world, and indeed the NHS, were all using Microsoft Office, and our dear friend Clippy, who I'm sure those who are slightly older will remember as the early little assistant who would say things like, "Oh, I see you're writing a letter. Do you want some help with that?" Fantastic little chap. But yeah, I mean, this sort of stuff with everybody now in offices, in the NHS. Word, Excel, PowerPoint, these are standard pieces of software. In fact, they're usually, very often, the only pieces of software that you are expected to use in many contexts. And as I said right at the start of the course, there's some concern about using Excel in particular for things that it's not meant to be for. Excel is a piece of software, it's a spreadsheet piece of software that is a very good piece of software for finance. But that's really all it was designed to do. But Excel has become a sort of, in particular, has become this sort of bespoke, do anything in Excel type of software. You know, doing advanced analytics in Excel, doing modeling in Excel. And it's not designed to do that kind of stuff. And even the government, you know, the Sage Group's been using stuff in Excel for some of the modeling. And you will have seen some of the stories last year around some of the issues that they had in the civil service with Excel and things being missed off because of limitations in Excel. It wasn't built to do this. It's a piece of spreadsheet software. And so if you take nothing else from this course, take that away, because really you should be thinking about the nature of the software you're using and what you're using it for. I think there are signs of change in the NHS in particular, and I think we'll come on to that in a moment. So that's kind of the history that most of us are familiar with and lived through. That, you know, that the home computers were seen as, you know, these fantastic fun little things in the 80s and 90s, early 90s, where we had the 8 and 16-bit computers, and they were fantastic in sizing. You maybe had a PC, and some people did, but most people had some sort of, you know, Commodore 64 or a Spectrum, and maybe upgraded to Amiga and Atari ST. And it was that, you know, we all went through that kind of path. Maybe you had an Amstrad CPC. We did for a brief time. But there was an alternative history that happened as well. And whilst Microsoft and, as I say, to a lesser extent Apple, but they have been around for a long time, were sort of slowly taking over the world. The idea that software should be open hadn't gone away. So whilst most of the world was being sort of swept along by this concept that we should be charging for software, and it should be something that's closed up, sort of a closed shop approach, this idea that we should have software and it should be free to interrogate and free to share and use hadn't gone. So in 1983, Richard Stallman, who was a member of the hacking community at MIT, announced the GNU project. Now, the GNU project, GNU stands for GNU is not Unix. It's one of those, if computer scientists, and I include myself as I am a computer scientist, have a slightly odd sense of humor, particularly when it comes to recursion, and they like to name things recursively. So GNU is not Unix is an example of recursive humor, because you say, well, what is GNU? And it just tells you GNU is not Unix. And so it's a particularly, if you're not a computer scientist, it's probably not that amusing. But basically, the goal of this project was to try and give computer users freedom and control over how they were using their computers, so they could, you know, copy, distribute, study, modify software however they liked, and trying to give them that control back that had been so rapidly taken away. And Stallman came up with these 4 principles, 4 freedoms. He saw in terms of software. So he saw freedom. He wanted freedom to see source code and use it in any way. Freedom to adapt the software for your own use. The freedom to share original software with others, and the freedom to share adapted software with others. So being able to see how something works, being able to adapt it however you like, being able to share those adaptations, and also being able to share the original software that somebody else wrote as well. Now, the GNU project started to get a bit of traction, but what it needed was an operating system that was free and open in the same way. There's no point having you know, sort of free and open source software and having these principles if you're then have to install them on an operating system that people have to pay for. It goes against the full freedoms. So what they did is they created an operating system called GNU that was based on Unix. And at the time, Unix was a proprietary operating system, fairly small scale compared to other OSs, but a proprietary OS, but which had some alterations to Unix. Remember, GNU is not Unix, as the computer scientists cackled. But GNU lacked one vital element which stopped it from becoming a full, proper operating system, and that element was the kernel. And you'll be familiar with the concept of a kernel in terms of Python, mainly because you have to restart it a lot. But a kernel is something in an operating system as well. Basically, it works in the same kind of way. The kernel is kind of the core bit of an operating system that controls all the hardware and software interactions. So it's kind of the beating heart of it that controls how the software interacts with the components you've got in your computer and manages all those complex processes. So that's a really fundamental part of any operating system, and GNU didn't have one. Fortunately, this character, and you can see from this photo that he's a bit of a character, stepped in. So this is the Finnish-American software engineer, Linus Torvalds, not particularly sociable chap. To give you one example of many, in a simple Google search, I will show you the many examples of how he perhaps isn't best described sociable. He once responded to some developers who created some security software that required an admin password to make changes. He called the idea mentally diseased, moronic, and suggested to the developers they should just kill themselves now because the world would be a better place. So he's a bit of a character, not particularly sociable. Having said that, if we just park his slightly odd character to one side, and you really should, if you want a bit of amusement, you really should Google some of the things he's written to people. It's quite astonishing. But in 1991, all parking everything else aside, he did do something that was rather wonderful, and he created the Linux kernel, which had freely modifiable source code. And in 92, the following year, he then licensed that project under the GNU General Public License, and therefore there was born the first truly free and open source operating system, where he created the Linux kernel, which would under the GNU public license, and so those two things came together, and suddenly they had an operating system that was truly free and open source. And this opened up huge doors in terms of the free and open source community in being able to use free and open source software on a free and open source operating system. Just as a side note, he also created Git, which you're going to learn about this morning as well. And there are jokes about whether Git is named after. So slowly, because of this, developers started to write free and open source software for Linux. And this started to take hold. People started to see the benefits of this. Not everyone, as you can probably imagine, at Microsoft was particularly a fan of this. So Steve Ballmer, who was the CEO of Microsoft in 2000, said they, referring to Sun Microsystems and Oracle, of course, are civilized competitors, but the Linux crowd are communists. So he didn't mince his words there. And then he didn't feel much better about it in the following year when he described Linux as a cancer. So they certainly weren't particularly enamored with this idea of these kids coming in and saying, hey, software should be open. Anybody should be able to see and adapt and share software. Why are you charging for this stuff? Why are you hiding your software? You should be able to freely share this. Microsoft didn't like it at the time. So where are we sort of today? Well, in 2009, the Linux market share, as you can see, I mean, if you just glance at this graph of the Linux market share, you might think, oh, that's a very encouraging growth until you look at the axis, the y-axis scale here. So in 2009, it passed 1%, quite a milestone, 1%. At the time of writing this session, it was at 2.38%. So it's grown, certainly grown. In fact, it's grown quite a lot considering from where it started. But it's clear there's also a very, very long way to go. You know, clearly we are still dominated, as we all know and wouldn't be surprised by most people who have Windows or Macs or whatever it may be. But there are signs of change, including from some of the most unlikely places. So Satya Nadella, who's the current CEO of Microsoft, is a big free and open source advocate, and has gone on record as saying he loves Linux, and he's very much trying to incorporate the free and open source ethos into what they do at Microsoft. And I think a lot of people were quite suspicious of that at the start, given the earlier comments from Microsoft about them all being a bunch of communists and that Linux was a cancer. But I have to say, I mean, certainly over the last few years, the actions speak louder than words, and they have done a lot of stuff that indicates that they are maybe serious about this. So we had the introduction of Windows subsystem for Linux. So you can now, if you've got Windows 10, you can run Linux programs natively in Windows. That's a big thing if you think about it. This is, you know, this is a company who had an operating system that people are paying for, most people in the world have, and they absolutely hated this Linux stuff because it allowed you, primarily, they hated it because it allowed people to run free and open source software, and they didn't like that. But now you can do that. You can do that in Windows. So not only have they tolerated it, they're now encouraging its use in Windows. In 2016, GitHub, which is the main free and open source software repository, which you've all used so far in the course in order to download the materials, but also hopefully in your project work, you'll be posting some of your work onto GitHub. So in 2016, GitHub announced that Microsoft were the single largest contributor to free and open source for that year. Again, that's a massive thing, considering where we come from. 2017, Microsoft announced that their cloud services, Azure, will now also run on Linux and will adopt free and open source SQL database systems. 2018, Microsoft switched from Windows to Linux for their new Internet of Things operating system. And also in 2018, Microsoft breaks up the Windows division, a sort of indication that they saw less importance in terms of having this big operating system that needs to dominate and that they need to charge for. This is a fantastic story as well, that probably many of you saw at the time. So 2019, Dr. Katie Bauman and her team created the algorithm Chirp, which reconstructed the first ever image of a black hole. All of that was done using free and open source software, including, if you look very carefully at this little image in the back, using matplotlib, which you learnt on Tuesday. So that's quite a powerful argument, I think, that something that is free and open source has been used to do something so amazing in the scientific community. So just to talk a little bit about our own history within the team. So certainly when we started out just over 10 years ago now, our team, we were primarily using, well, exclusively using actually proprietary software. So a lot of the work we were doing using a piece of software called Simulate, which is a piece of software for building discrete event simulations. Very nice piece of software, generates some excellent visualizations. We were using, certainly I was using a little bit, NLogic, which is a piece of software that does a number of different modeling types, primarily targeted agent-based simulation, which was my background. That's what I did my PhD in. We had iThink and Stella from IC Systems to develop our system dynamics models, and Excel for in terms of cost effectiveness, health technology assessment models, which we did a little bit of within the team. And indeed, the very first HSMA program back in 2016, we were still using this stuff. So we taught and we focused the very first HSMA around discrete event simulation. So they were all using Simulate. The problem started to emerge. There was sort of two things that happened within the team. The first was that at the end of that very successful pilot of the HSMA program, there was, we had an evaluation of it. It was considered to be a great success. We had various recommendations for sort of how we'd evolve it in the future. But one of the key things that came back was, we'd love to use this stuff, but Simulate costs $3,000 a license. We just don't want to invest in something like that. And so there was this real barrier. And I think out of the 6 organizations, I think one of them bought a copy of Simulate. The other thing that happened was, in a team, I guess, we had a lot of self-reflection and thought about what we were doing, and we had a lot of success, particularly in the early days, in terms of working with people on collaborative projects. And one of the key things that we kept getting asked for was, "Oh, great! Can you share the model? Can you share what you've done?" And we'd have to say, "No, we can't, because it's been built in a proprietary piece of software. Hello, sorry, can you mute yourself? Yeah, so we had to say that we couldn't share it because it had been built in this proprietary software. Now, there are ways in which you can share simulate models. It does involve more money, and you have to pay for a service in which you can share, to a limited extent, models with somebody that doesn't have simulate installed. But that's not ideal, and we started to think about this and question if we are scientists and we are conducting research that's affecting people's lives, and people are rightly asking to see what we've developed that are coming to these decisions and generating this evidence, should we really be using stuff that we can't share? And so that, combined with the feedback we got from HSMA, caused us to rethink and evolve our thinking within the team to consider using free and open source approaches instead. And indeed, I always feel quite kind of sorry for the HSMA 2 cohort, who were a brilliant cohort, but they were live, literally live, as we were going through this process. So they started at the very start learning Simulate. We even had somebody who came down from Simulate to teach them. And then we suddenly, as we started a pivot, we started showing them JamSim, which is like Simulate, the visual interface, but is free and open source. And then we started moving towards what you're going to be learning on Tuesday, SymPy, and starting to do a lot more Python development. And so they had probably the most eclectic training course in terms of all the different ways in which you can do the same thing. But they were fantastic. They really tackled this really nicely. But there was a definite sea change, and particularly since around 2018, so the last 3 years really, we have now completely switched to using free and open source, both within the team and within the HSMA program. So last year, HSMA 3 was the first time we had totally free and open source approaches to it. And we saw that not just as a benefit in terms of the fact that, people, organizations didn't have to invest in software and pay for software in order to keep using this stuff, which we already knew was a big barrier, but also because we thought, well, it's the same principle. We're teaching people how to do the kind of stuff we do, and it's going to have the same kind of impact. But hopefully that's the point of doing this. That's the point. That's why you're all here. We're teaching you things that will allow you to have an impact, and hopefully a positive impact on patients, on service users, on your organizations. And so if we're doing stuff like that, if you're doing stuff like that, then really shouldn't you be doing stuff that can be interrogated and that can be questioned and properly reviewed? And so that's kind of our motivation, both as a team and for the HSMA program, for moving towards free and open source software. And there are signs that things are changing in the NHS, very, very definitely. It's still, I don't want to single out the NHS other than the fact that, most of you are working for the NHS, and that's why I mention it. Many organisations are the same, but obviously there's still that dominance of we do everything in Word and Excel. But things are changing, and you'll have already seen it. I mean, many of you I saw when you applied for the programme had skills in R. That's a relatively new thing that the NHS is pushing for the use of R, which is a fantastic thing to see. We've got the NHS England Open Source Programme, more information about that at this link as well, and NHSX as an open source organisation. And I love this quote from this particular link in particular, which said, the public have a right to see the code we create. They have a right to understand the algorithms we use. They should be able to examine the code for flaws and be able to suggest improvements. And it's absolutely right. It goes to the heart of why you do free and open source development, particularly for things like science and things that affect people's lives, which all of you are going to be doing. So as HSMAs, I think it's really important to sort of reflect on what we've been talking about, think about why you're doing this, what the purpose of this is, and to really reflect on the fact that you are going to be building stuff, either models or algorithms or whatever it may be, but whatever you do, the whole point is that it's going to impact the lives of people, and possibly very significantly. And so they have a right, they do have a right to be able to interrogate why your models or your algorithms came to the conclusions that they did, why you generated that evidence that then went to the policymakers, the decision makers, and they made those decisions. They have a right to see that. They have a right to question that. That's not to say, you show them patient, non-anonymized patient data or anything like that, but they have a right to see that the methods that you use and the models that you generated to come to that those conclusions. And also, you should be looking to spread good practice, and you should be looking to share your work to allow others to benefit. If you've developed a fantastic model here that is able to, very efficiently sort out, I don't know, an ophthalmology department in terms of some of the particular quirks of that kind of department, you should share that. Other people should benefit from that. We don't want to be in a world where everybody has to then reinvent their own wheel. And so I sort of leave you with the words of Richard Stallman. It's a wonderful quote, which I think has a lot of power, particularly when you think to how this reflects on what you're doing, what we're all doing, to be generous with knowledge, share it freely, and give other people the freedom to share it freely as well. And that's really important. And whilst you reflect on that, we're just going to have, via courtesy of Richard Stallman, a short musical interlude.
Join us now and share the software. You'll be free, hackers, you'll be free. Join us now and share the software. You'll be free, hackers, you'll be free. Hoarders can get piles of money, that is true. Hackers, that is true. But they cannot help their neighbors, that's not good. Hackers, that's not good. When we have enough free software at our call, hackers at our call, we'll kick out those dirty licenses evermore, hackers evermore. Join us now and share the software. You'll be free, hackers, you'll be free. Join us now and share the software. You'll be free, hackers, you'll be free.
And if ever you had any doubts that HSMA is some sort of cult and I'm a cult leader, now I think those thoughts can be very much put at the forefront. And yes, you're probably right. So apologies, a slightly odd song, but I think nicely summarises the point, even if slightly weird, that actually we should be thinking about, particularly in the kind of work we do, about how we can share things and how we can share the knowledge and also make ourselves open and transparent. So after that song, by the way, you will get that song stuck in your head for some time. It's one of those very, very catchy songs. I don't know if that's in a good way. I'll leave you to decide. So enough of me talking. I've been sort of spouting the wonders of free and open source at you for 40 minutes. What I want you to do now in the next half an hour is to go into your groups, and I want you basically to have a chat about some of this stuff. So I want you to particularly, just have a general chat here, but particularly around these sort of three main questions. So can you think of current or historic examples where the use of proprietary software or closed approaches in some way has limited collaboration and sharing, either within your organization or with other organizations? Also, what do you think are some of the key areas where a movement towards a FOSS ethos in your organization could lead to a real benefit? And thirdly, how would you like to see your organization embrace FOSS in the future? What are some of the challenges you envisage with that, and how might they be overcome? So I want to just have a bit of a chat, bit of a discussion about this stuff before we get into the technical stuff in the second half of this this lecture, where we look at Git, as they named after Linus. So I'm going to give you half an hour and then also take a 10-minute break. So it's 10 past now. So if you do this till 10:40 and take a 10-minute break, we'll come back at 10 to 11 and I'll hear a little bit about what you've been discussing, and then we'll move on and we'll talk about Git. Okay, have fun, and I'll drop in on your discussions. Okay, so welcome back. It was fantastic hearing some of the things that you were talking about in your group. Some really good discussions about free and open source software and some of the challenges that you've had and some of the challenges you can foresee, and lots of talk about how you see some of the benefits and how you see things are changing as well. So I'm just going to pick on a couple of groups just to share some of the things that you've been talking about, some of the key points. I think there are wide interest in that, and so to enable me to do this, we are bringing back the much loved wheel of names, and so it's time to spin the wheel. Now there was some concern that the wheel of names wasn't quite as random as we thought, so I'm going to randomly click shuffle a few times just in case it's not that random, and I suspect it isn't. And let's spin the wheel and see who's picked. Ooh, this is close. Oh, no, it's Robocop by the look of it. Somebody from Robocop. Fantastic. Okay, someone from Robocop, can you share what you've been talking about, please?
We didn't fully nominate a spokesperson, but I made notes, so I think it will be full to me. We struggled to think of examples around data sharing necessarily or collaboration, but we did sort of hone in on patient systems and how NHS organizations seem to have had a history of maybe getting stuck with lengthy contracts with systems that don't quite do what you want them to do or are a bit rubbish, and then you're stuck with it for another 10 years. And that maybe that was something that if it was open source to be able to interrogate and see that, but obviously then companies don't want you to be able to see if it's a bit buggy or, you know, lose out on their profit motive there. And also Power BI was something else that obviously organizations are starting to adopt, I think, where the full version can be quite expensive. So you have a free version which has limited functionality, and then when you come to start sharing it, it then starts getting very expensive with some of the licenses that are needed. Yeah, those were the sort of two examples that we came up with.
It's really good. And yeah, I think Power BI is the other sort of big one that we often hear sort of talked about in the same breath as Excel as well. And you know, I think certainly the cost issue is quite an interesting one, and maybe a way into certainly for HSMA that's been a real benefit in terms of us, you know, selling the benefits of this sort of stuff. And then of course, I think when people can see you know, the benefits of sharing, particularly, you know, when you've got a global pandemic and people are all faced with the same kinds of challenges as well. I think that's a really important sales point as well. So fantastic, great, thank you. Okay, let's apologies, I accidentally clicked my mouse and spun it again, but I've ignored that one. So let's click again and see what we get. Oh, looks like it's going to be Skynet. Yeah, it's Skynet. Okay, somebody from Skynet, can you share what you've been talking about?
Yeah, I don't mind. I took some notes. Yeah, we talked similarly about patient systems, particularly like EMRs and integrating different softwares together and having to get the supplier to link it up, which is an additional cost. We talked about being restricted from doing this course by not being able to have certain softwares downloaded on our work computers. We talked about unsustainable spreadsheets as an opportunity, as possible opportunities, so different process flows and things that are being done on spreadsheets. And then we talked a lot about the challenges. So we talked about the need for training and resources and the lack of technical staff, or whether it is a lack of technical staff or whether it's a lack of technical staff who will work on NHS salaries. And then we talked about security issues or perceived security issues, so people not fully understanding open source software. And then we didn't really get to ways to overcome it. We did talk about student, like undergraduate student exchange programs and internships, potentially as proof of concept developers. But yeah, I think that was mostly our conversation.
Really interesting. I think those are really nice ideas. Actually, some of the student internships and things like that, where you can actually, and in similar vein to HSMA, where you're actually showing a demonstrable benefit internally within that organisation. I think is always a good. So I mean that's been our sort of ethos throughout, even before HSMA. That's how we sort of gain trust in terms of working with people and showing the benefits of what this sort of stuff can do. And you raise a really interesting point as well about the security stuff. And that's something we hear quite a lot. And of course, and I did hear one of the groups talk about the irony is in that, a lot of the security issues that have been faced in the NHS are security issues in proprietary software. And so it's always very odd that people seem to lock down on, we must trust these big proprietary pieces of software that you can't interrogate and don't know what's going on underneath, and which are the key targets for security violations. So I think
it's delegated responsibility, at least at our place. They want someone else to take that responsibility rather than manage it ourselves.
I think that plays in a big part of it, very much so. And I think there's a big part of the fear of the unknown as well, that people who are not used to this kind of software, and you almost think if we give you Python, are you suddenly going to hack our systems? It's that kind of thought, which you can understand, and it's that process of gradually trying to build confidence in why you're using these methods, that actually they're safe and what you can and can't do with them. I think is really important. Fantastic, thank you very much. Fantastic discussions. And lots of really interesting stuff that I heard come up from there. So hopefully it's been a good sort of thinking point, really, just to get you thinking a little bit about free and open source and why we're doing things in this way, and particularly as you go into your projects, the sort of mentality that's good to adopt for this kind of thing. So hopefully you will all be developing free and open source solutions that in your projects that will be shared as they're happening for HSMA 3 as well. Okay, so let's move on to we're going to pivot slightly and move on to the second bit of today's lecture, which is talking about version control. And we're going to talk about specifically Git. So you'll all be familiar with GitHub, if nothing else, because that's where you're downloading the lecture materials for this course. But GitHub is the world's largest online repository for hosting open source code projects, and just touching on what we talked about earlier, is now a subsidiary of Microsoft since 2018. So demonstrating the real change or apparent change in the way in which Microsoft are working. And GitHub basically allows users to work together, collaborate on projects, and share modifications. And so it's a fantastic widely used collaborative tool. And at its core, GitHub has Git functionality. It's built on Git, which allows for version control. So we're going to talk about, in this session, version control in Git. We're not going to talk about GitHub in this course, but I am going to link you to some materials that will show you how to use GitHub. If you know Git, it's very easy to use GitHub and to make that extra step. But so the primary thing really is to talk about the version control in Git that underpins this. But it would be fantastic to see all of your projects being put up on GitHub. That would be an amazing thing to see. So as I mentioned earlier, I just want to say particular thanks for this bit to my colleague Tom. It was quite funny. So Tom had to write a session on Git for our MSc in Applied Health Data Science. And there was kind of a standoff who was going to write their Git session first. And I think Tom drew the short straw. I held out and he wrote his, and I, in true free and open source spirit, nicked it with his full consent, of course. So much of what I'm going to tell you now is based on his excellent materials, and I will link to those materials so you can see the original stuff that this is based on. Tom also goes into a few extra little things as well, and I'll also again show you some other fantastic online resources for this kind of thing. So what do we mean by version control? Well, version control refers to the tracking and managing of changes to code. Why is that important? So let's just think about some examples. So let's imagine that you've been asked by your organization to take over a project that was undertaken by one of last year's HSMA. So that could happen. So here are some of the files that you've been given, and you've been tasked with trying to work out which file you think you need to use. So we've got all sorts of files here. We've got a 2019-0320 main version 2.py, a v2 main 2019-0320.py, v2 v3 main final tm-mpma dcma conflicted copy, etc., etc. And we've also got this archive folder, and in there we've got all sorts of other things. And I suspect that you're all looking at this and thinking, yeah, I've seen this sort of thing before. This isn't beyond the realms of reality. We've all seen cases where we have probably Excel spreadsheets that say version 3, definitely the final one. I mean it this time. No kidding, gov version. I mean, this is a widely used thing. This is not good practice if you're a coder. This is very bad practice. Okay. Let's also imagine a different scenario. Let's imagine you've been given some code by an analyst who's long since left your organization, and you can see from the comments in the code that the code's been modified by multiple people over many years, but you don't know how many times, you don't know who's made the changes, you don't know what they did, and you don't know why they did it. And it's your job to fix it. Where on earth do you start with something like that? And in reality, what you'd likely have to do is go over the whole code to try and work out what is happening and why it's not working as expected, because you haven't got that full traceback of the changes that were made and why and by who and when they did it. So these examples, which, as I say, some of them will probably ring true for you even in non-coding contexts, show us that we do need something to help us. And specifically, we need something that will help us track what changes have been made, when and by who, and something that will enable us to manage the versions we have, so we always know which is the latest version, what the previous or alternative versions represented in terms of the changes they contributed to the development, and that we can switch between versions that we know what these versions represent as needed. And to enable us to do this, we can use a version control, piece of version control software. There are many out there, but one of the most widely used by far is Git. So Git is a word that very often describes me, I'm sure, but it is also a distributed version control system that is very widely used in the development community. Now, what we mean by distributed is that the complete code base, what we mean by that is all of the code, all of the there's Python, all of the Python programming code that you put in, and its history, all of the changes that have been made and by whom and when, all of that is mirrored on every computer for every developer on the project, rather than just being centrally held. And that's what a distributed version control system gives you. So that means everybody who is a developer on the project and is contributing has all of it. They have all of the code base, all the changes, and it's all stored on their computer. And then when we want to bring things back together, we do something known as a merge, and we'll come on to that a little later. And that's when we bring things back together. But that's what we mean by distributed version control system, which Git is. So this is the sort of broad process for how we make what's known as a commit to Git. I am fully committed to being a Git, just as an aside. So we have this central idea that we have a repository, and the repository basically holds the complete history of all of the files in the project and all of the changes that were made to those files. Okay, so it's got all our code and all the changes that were made. And that's all stored in the repository. So on GitHub, when you're accessing the lecture materials, there's a number of different repositories that I point you to. And so each of those repositories basically holds all of that information. So let's imagine we've got a simple .py file here. I've just got my example.py. What we would do is we would make changes to our file and save it. So maybe we're in Spider, we're doing our coding, we change our file in whatever way we want, and we save it as normal. Then we want to add it to the repository. So the first thing we do is something known as staging. And by staging the file, we're basically telling Git that we want our file, or more specifically the changes to the file, to be included in the next commit to the repository. Okay, so this process is known as staging. We're essentially giving Git the heads up that there's some changes I've made, and I'm going to commit that to the repository. After we stage the file, we may, of course, go back and make changes to other files that we've got in our repository. And then once we're happy and we want to commit all the changes that we've made to our file or files, then we make this commit, and that's committing the changes to the repository. And what that does is it creates basically a snapshot of the code along with the log of changes which detail everything that was changed and who did it and when they did it. And that log gets created as part of the stage process. So we've got our file, we make and save our changes. We then stage the file to give Git the heads up that this is incoming. And at that point, Git will create this log of changes. And then when we're ready to commit this to the repository as this is now an official change that we want to make, we commit it, all of the changes that we made to all of the files that we've staged, and that creates a snapshot in time. So I'm going to show you, because much of this session I'm going to be walking you through how to do this, and you'll see how this works in practice. So as I say, a commit represents a snapshot in time of your file or group of files. And basically what Git does is it tracks the changes in each file between commits in terms of the things that we've added and the things that we've removed. So if you've got your example.py file, it'll track you've added these lines of code and you've taken away these lines of code. So at a very basic level, that's what it's doing. And what that allows us to do is we can really easily then see what changes were made, when those changes were made, and who made those changes. And that's really important because, as we've just discussed, if something goes wrong after a change was made, we can more easily see the point at which we need to revert back. We can see where the problem emerged, who did it, why they did it, when they did it, and so it becomes easier to revert and to fix it. And we can view the changes between specific commits. And in Git, this is known as the difference, or more commonly, the diff. So the diff represents the differences, the changes between specific commits. So a diff file might say, this is these are the lines of code that were added, these are the lines of code that were removed. So let's think about really simple examples. As I imagine, I've got a piece of code here that I start with, which just sets up a very simple list called my list. And I've got a really simple loop here that just loops through the list, takes the modulus, takes the number modulus 2, sees if it's 0, and then obviously that's working out if the number's even or not. And if it is, then it prints a little message. Let's imagine I stage and commit that file, but then I go in and make some changes to that file. So I go back to my file, and this time I've added in an import statement here, and then I've also made some changes to my for loop. Once I stage and commit this, the diff will appear in this way here. So the diff will indicate the things that have been added and the things that have been taken away. So you can see here, we've got these little plus symbols saying that import random was added in this blank line here, and all this stuff in the for loop was added. But then also this line here where we've got print the number is even, that was taken away. We wrote something a bit different down here instead. So it's very clearly, we can see at a glance how that we went from one version to another and the specific changes that were made. So as I say, what I'm going to do, I'm going to walk through a simple example for most of this session. So what I'd advise you to do, just for now, just follow along with what I'm doing, watch what I'm doing, and listen to what I'm doing. And then you're going to get a practice after I've done this to have a go at doing very much this yourself. So just a little word before I start. If you're using Windows, when you come to do this yourself in the exercise, you access the Git command line by opening Git bash. So if you've installed Git as per the instructions, you should have an option to open Git bash. And that bash, by the way, stands for Born Again Shell. It's a Linux term. Those of you who used Linux before will be familiar with it. If you're using Mac OS or Linux, which are both Unix-based operating systems, then all you do is you simply open a new terminal, assuming you've already got Git installed. If you're using Linux, then odds are that you have got Git installed. It normally is installed automatically. It's one of the great benefits of Linux for development is that things like Git are integrated automatically. But if you use Mac OS, as long as you've installed Git, you'll be able to just open the terminal and that will work. And basically what we do is we interact with Git by issuing commands in the shell or terminal. So those of you who are old enough to remember DOS and using DOS command line, and maybe even older, going back to the old Spectrum and Commodore 64 days, will be well used to the days before you had all these luxuries of graphical user interfaces. So we're going back to that with Git. You're going to be using the command lines in order to interact with it. Now, if this is the first time that you've used Git, which I suspect will be the case for many of you, the first thing that you'll need to do when you before you start the exercise later is you'll need to specify the username and email address that you want to use for your Git account. And it's recommended that you use the same username and email that you're going to use, or if you're already a GitHub user, that you have used or are using for GitHub. It just makes things easier, because then if you go on to use GitHub, check for your will, then you can use those same details and it can integrate nicely with what you're doing. So the way you do this, I've already done it because I'm already signed off, is you use these two commands in either Git bash or your terminal. You type in Git Config, then 2 hyphens to indicate an option, global, user.name, and then inverted commas, you put whatever you want your username to be. By the way, these are not my real details. This is obviously because this eventually will be going out on YouTube publicly, so I don't share my actual email address, etc. So my username is not Dan is awesome, although maybe it should be. And then we can set up the email in the same way, just by using user.email and put in whatever email address you want to use. So you'll need to do that the first time. If you've not used Git before, you'll need to do that as the first step. Okay, so then assuming you're all set up with Git with the username and password, one of the first things we then need to do is to set up our Git repository. And what we do is we navigate to the directory that stores or is going to store our code for our project. And then once we're in that directory, we call the command git init. And that basically means initialize a new Git repository in this directory. Now, if it's a new empty directory, it'll just create a new empty repository. And in many cases, that's probably what's going to happen, because hopefully you're starting to use Git right away with your new project. So you create your new directory, and then you're going to set up a new empty repository. If there are files already in there, what it'll do is it'll note that they're there, but it's not going to begin tracking them for future changes until we tell it to do so. So we have to actually tell it, and we'll show you how that works in a bit. Now, just those of you who used DOS in the past, or have used Linux or Mac OS terminals, will recognize some of these commands, but we're going back to the old way. So if you want to switch directories to get into the directory you want before issuing this git init command, then you can use these kinds of commands here. So ls is the kind of Unix-based command, or dir. You can use both. Either of those will list the contents of the current directory. cd stands for change directory. So if you put cd test, then that will tell it to change into the directory called test. It is in the current directory. And cd ... basically means go up a level. So you go up to the parent directory. So that allows you then to sort of move up and down your directory structure. Mkdir, makedir, which stands for make directory, and then the name of directory creates a new directory, new folder called whatever you've named it. So in this case, test in that current directory. So let me switch out. I'm going to open up Git now. I'm going to slightly cheat because I can on Linux. And I don't know if you've got this option actually in, I think you may have in Windows, I'm not 100% sure, but I'm going to open straight into the directory I want to go to. So this is my folder for the training session that we're delivering here. So I'm going to open my terminal there. So I'm already there. I don't have to worry about navigating there, but I'm going to create a new directory. And I'm just going to call mine live proj, just for purposes of this. So I've now created a brand new directory called live proj, which you can see there. And then I'm going to change into that directory. There we go. So I'm now in that directory. At that point, because I'm now in the live proj directory, this is a brand new directory that I've just created, so it's empty. I'm going to then initialize a new GitHub, a new Git repository. So remember, we used Git init, rhymes just to help. If I type that, push enter, and it tells me that it's initialized an empty Git repository in this directory. So now there is a Git repository, and I can start using Git in this folder and all the subfolders. Okay, so that's the first thing you need to do whenever you set up Git. So the first thing I'm going to do is I'm going to add a very simple .py file to my repository. I'm going to show you how you stage and commit that file. So I'm going to switch over to Spider now. I'm just going to open a new terminal to do that. Close these down. Okay, so let's just write a really simple piece of Python code. It's just going to have a single function in it called add numbers. Takes as its input 2 numbers. You can probably tell I seem to like building calculators based on your recent exercises. And then I'm just going to have the function that basically just adds those numbers together. And then returns the result. Okay, simple piece of code. There we go. Now I'm going to save that, and I'm going to save it into my directory where I've set up my new GitHub repository. So to be, and then live proj, and I'm just going to call that myculk.py. Okay. So I've now got in this folder, and we can see it. If I go into it, I can see I've got a folder now called live proj, and I've got a file called myculk.py. Okay, all straightforward so far. So because I've now set up a Git repository, at any point I can use something called the Git Status command to check the status of the repository. And by status, I mean looking at the files that have been modified, ones that are ready to be committed, etc. And so if I do that on my new repository, here, so if I type Git Status, now this is a common command that you'll be using all the time. You should be checking the status of the repository frequently as you're using Git. So if I hit enter there, we can see it gives me various information. It tells me what branch I'm on, and by default I'm on the branch called master. I will come back to branches a little later, so don't worry about that for the moment. It tells me that there are no current commits yet, but it has picked up here that there's an untracked file. So it's picked up there's a file in this directory called mycog.py, and I haven't yet told Git to track that in any way. So it's just letting me know there is a file in this folder. You haven't told me to track it in any way, so I'm not going to, but I'm just letting you know that file is in there. Okay. And obviously, if you've got multiple files that aren't yet being tracked, they'll all be listed there as well. Now, Git won't track any changes into any of the files until they've been staged at least once. Once you stage a file at least once, from that point forward, Git will then track any changes that are made to that file. Okay, all straightforward so far. So next, what we want to do is we want to stage our file. We want to tell Git, give Git the heads up that this file needs to be included in the next commit. That will also tell Git that we wanted to start tracking changes to this file, which remember, at the moment it's not doing it, it's just ignoring it. It's just saying, I can see there's a file there, but I'm not doing anything about it. And the way in which we stage a file is using the Git Add command. So we say Git Add and then the name of the file. And we can also use various other patterns here. So we can say Git Add and then a full stop, and that will say add all of the files in the current directory. So it'll tell it to stage everything that's in the current directory. Or we can add all of the files that have a certain file type. So if I wanted to stage at once all of the .py files, for example, that are in the current directory, then I can say use the asterisk here as a wildcard and say asterisk.py, and that will say everything with the .py extension. So let's call Git Status. Let's first add the file. That'll help. So I'm going to stage my mycog file here, because remember it's not being tracked at the moment. So the first thing I'm going to do here is I'm going to say Git Add to stage the file, and I want to stage the mycog.py file. So if I do that, it appears nothing has happened. But if I now type Git Status again, and remember this is something you should do regularly, we can see there's been a slight change now. So we're still on branch master, still no commits. I haven't committed anything yet, but it's picked up that there are changes to be committed. And the change is that there's a new file, because remember, this is the first time Git has been told to track this. So there's a new file that's about to be committed to the repository. So it's picked this up here and said there's a new file, mycog.py. Remember, we haven't actually committed anything yet. So we're now ready to commit our file to the repository. Now, when we commit, we need to supply a commit message. This is compulsory. And basically what a commit message is a short description of what the commit represents. In other words, what you've done, what you've added, what you've changed, what you've taken away, etc. Now, this is really important because, as we said before, part of the reason why we want to use version control is we want to be able to track and understand exactly what changes were made by who, when, and why they did it. So the commit message is a really important part of this. Now, commit messages ideally should be very concise, but they should also be specific, so that someone else, or even if it's just you doing this project, and you're coming back to it later, you can understand what this snapshot, what this commit represents. What is this? So obviously in this case, we're just creating a new file. But if I then went back and changed it in some way, I need to have a concise but specific message that indicates what I changed, so I can understand, oh, that commit was where we added that function, for example. And a good tip, and again, thanks to Tom for this tip, which I believe in turn he got from someone else, is that you might consider splitting your commit message into two parts. So the first part representing the type of commit you're making. So is it an initial upload of a file? Is it a bug fix? Is it an upload of some documentation, etc.? And the second part, which describes the changes. Okay. So for example, if we have the commit message init :add mycog.py, that could then clearly tell us, well, this is an initial upload of something, and the thing that was initially uploading was I'm adding mycog.py to the repository. So that's very clear, and I can understand that. Now you can use whatever style of message you like. There are no sort of standard conventions, But however you do it, you should make sure it's consistent, and you should make sure that somebody else, or even yourself, when you come back to it, could understand it. So you need to, and using a consistent style will help because people can understand what these messages represent. But you do want them to be concise. You don't want to put paragraphs of text here explaining what's happening. You just want a very concise, specific description of what was done. So, a little bit of a word of warning, which I believe I mentioned before when I was talking about Git and installing Git. So I said that Git requires a commit message. It's compulsory. If you don't supply a commit message when you make the commit, Git will take you into a text editor and it will force you to write that message. And if you don't, or you refuse to do so, it will not make that commit. Now, if you're using Windows, which many of you are, and you ignored the warning that I gave you about when you install this, you probably should change the default text editor, you might find yourself in a rather hardcore text editor called Vim. Now, Vim, as I mentioned before, is incredibly difficult to use. It's infamous for being incredibly obtuse and very unfriendly. You will find that out immediately if you accidentally find yourself in Vim, because it's very difficult to even exit the program. And that becomes a problem when, if you haven't changed this, you forget to input a commit message and you'll get taken to Vim and you'll have no idea how to get back out of it. Okay. If you don't believe me, there are books that you can buy that have been written about how you get out of Vim. It's that difficult to use. But some people swear by it. I am not one of those people. If you are one of those people, great, in which case go for it, have fun with Vim. But if you're one of us normal people, I would advise that you use one of the alternatives. So if you haven't already switched that, there are instructions for how to change from the default of Vim to Notepad++, which is a much friendlier alternative, at this link here. Hopefully you've all had that changed when it was installed, but if you haven't, do that first. It's very simple to change it, and this will guide you through how to change that. But I would strongly advise you not to use Vim unless you know what you're doing. So do make sure. It's very odd that it defaults you on Windows. It's like, I'd almost say it's some sort of cruel joke that they get you to use Vim by default. I believe it does it on Mac as well. That's somebody pointed out recently. So we've got our file that's been staged, my cult file. I need to commit it now. I want to add a commit message. Now, the way I can do this, I can just use the command git commit, and that will create a commit. And if I add the M option here by putting -M, that tells us that we want to add a commit message, and then we can give the commit message in inverted commas. Now, as I say, that is compulsory. So if you don't put that in and you just type git commit, then what will happen is it will take you into the text editor and say, well, what's your message then? So if it's successful, you'll get some sort of message like this saying that the file has been changed and there have been so many insertions, so many deletions, etc. So let's try that with our file. So when I call git commit, this will, all of the files that have been staged, we've only got one here because we've only got one file so far. All of the files that are staged will be then committed. So these will be permanent changes. A snapshot will be made, and we're saying we want to make these changes to our repository. So I'm going to say git commit, and then I'm going to add a commit message here. And I'm going to use the style I said before. So it's an initial upload of a file, and I'm just going to say that I'm adding mycolg.py. So if I hit enter on that, we can see it comes up with this information here. Again, telling us what branch we're on. We'll come back to that. One file's changed, 14 insertions, etc. Okay. So that's what we've done. We've now created a new file. We've saved it. We've then staged it using Git Add to tell Git that there's a file that we want to add to the next commit. And that will then start tracking changes. And then we've said we now want to commit. So these changes need to be made to the repository. So again, let's use our Git Status command to have a look at what's happened now. And again, you should always use Git status regularly before and after stages and commits to see what's happening and what your repository looks like. Particularly as you get with more complex projects, you want to get a good handle on what everything looks like. So if I type Git status now, before it was telling us that there were some changes ready to be committed. Now it says on branch master as it did before, and it says nothing to commit. The working tree is clean. Now clean basically in Git language just means there's nothing staged, i.e. waiting to be committed, and no files that have been modified that haven't already been committed. So if I were to then go back into my calc now and change it, because Git is now tracking it, if I save those changes, that tree will no longer be clean, it will become dirty. And so then it will say there have been changes to this that have not yet been staged. So we'll go back to how we were. Okay, but this working tree clean means there's nothing, you've committed everything that's been staged, and that there've been no changes to anything that I'm tracking prior to after that. Okay, so Git Log is another really useful command that allows us to view complete or partial history of all of the commits that we've made to our repository by viewing the log. So when I type Git Log, the key information that will come up is this. The first thing that will come up here will be what's known as the commit identifier. Now every commit has an identifier, and basically it's just an ID number for that commit. And that's really useful because it allows us to refer to a specific commit. For example, if we wanted to revert back to that version, back to that commit, or if we wanted to look at differences between two different commits, we need to tell it which commits we're talking about. And so we can use the identifier there. Now over on the right, we can see that we've got this which says head, and then an arrow, and then master. Now head basically means that this is the latest commit in this particular branch. Don't worry about what a branch is for a second. Again, I'll come back to that in a bit. Now we've only got one commit so far, so it's going to be the head by default. But the head basically means this is the latest commit in this branch of development. Then we've got the author information, which will give my username. So this is my username, which you'll have seen, HSMA master, when you go onto the GitHub, and then my email address, which obviously you all have. I've just redacted it here because this is going publicly on the internet eventually. And then it'll give the date and time that the change was made. So this ticks the box of knowing who made the change or changes and when they were made. And then it also gives the commit message, which if we've been good with our commit messages, will then describe exactly what was changed. So this information in the log gives us lots of useful information and the purpose of using a version control. It tells us whether this is the latest commit, the branch of development, the ID for this commit, who made the changes, when they were changed, and the nature of the changes in terms of the Git commit message. So if I do that on mine here, I type Git Log, you can see that's what comes up. And obviously the number will be slightly different to the one here because that was a different repository when I was writing this. So we can see that's what's appeared here. Okay, so Git Log is really, really useful. Now, in practice, when you're committing stuff to a Git repository, it's very good practice to try and avoid having large commits that have large numbers of changes, because that kind of defeats the object of using Git. Because it makes it really difficult to follow. If you've committed, say I committed that file there, and then I go ahead and write another 500 lines of code that has another, sort of 50 functions in it, and then I commit that not only am I going to have some fun trying to get a short, concise Git commit message, but also that's going to be really difficult for somebody to follow what changes were made. Okay, so what you want to do is commit often with smaller changes. So you make small changes and then you commit. You keep committing regularly, and each time you make a small change, you then commit. Now you don't want to go too far down the other end of the spectrum. Don't start committing every time you add a line of code, for example. Once you've done something small but meaningful, so maybe you've added a function, maybe you've added a class definition, that's the point at which you would. So once you've something atomic that you can describe, like a new function, new class definition, a new bit of your code that will do something. That's the point at which you should then commit, and you should commit regularly. Now, because of that, because that's what you should do as good practice, you'll very often have very large commit histories because you're committing very often. Whilst the Git Log command is very useful, we probably don't want to see the whole history every time we view the log, particularly as we get through development of a bigger project. There could be hundreds and hundreds and hundreds of commits. We don't want to view all of that every time. So we can use various options on the Git Log command so that we can just view a partial history. So if we say, for example, Git Log -2 or -2, that will tell it to view the 2 most recent commits, and you can change that number to whatever you like. We can also use Git Log with the one-line command, and that will tell it that we want to view the history, view the log, but with each commit as a single line with condensed information. So rather than having all of that information there, we just get that as a condensed form, so 1 line per commit. That's a really useful way of viewing the log because it also gives us a 7-digit version of the commit identifier. So rather than having to give this very long number every time we need to specify a commit, we can just use the first 7 digits, and in most cases that will be enough for it to recognize, and that's standard practice. You typically just use the first 7 digits of a commit identifier to identify that particular commit rather than using the whole thing. And you could just copy and paste or manually type the first 7 digits from this. It's much easier if you've got that in the 1-line option where it's already given it to you as the 7-digit version. And you can combine those things as well, so you can have a 1-line version of the log, but for the last 2 commits or whatever it may be. So let's make some changes to our code and commit the changes and see what happens. So let's do something a bit more interesting than just adding a brand new file. So what I'm going to do here is I'm going to add a subtract function to my code, my mycalc code. So let's go back to Spider here. So I'm going to add a new function, def subtract numbers. Again, this will take in 2 numbers as the inputs. And then I'm just going to have result equals num1 minus num2, and then return the result. So a nice simple function. First one was adding, second one taking away. Very simple. So I'll now save that. So now save that file. So once we've saved the changes to our file, we should go back and have a look now at the status of the repository. Now remember, before, when I did this a second ago, it said that the working tree was clean. So let's see what appears now. So if I type in Git Status. Okay, so now it's picked up that the tree is dirty now because there have been changes that have been made. Remember, it is now tracking mycalc.py because I staged it, and by staging it the first time, it will now forevermore track that file. And so it's picked up that there have been changes that have been made to this file that have not been staged or committed yet. Okay, and it also picks up that I haven't staged anything ready for commitment, so no changes added to commit. So that's really useful, telling us something has changed, but nothing is going over to the repository yet. So let's again stage the file using Git Add, and we'll have a look at the status again. So if I type Git Add mycalc exactly the same way as I did before, and let's have a look at the status again now. And we see now it's come up in green because it's picked up the changes to be committed are in the modifications that have been made to mycalc.py. So now it's saying, okay, we've picked up that the mycalc.py has been modified and that these changes have now been staged. So the next time I call the git commit command and commit changes to my repository, this will be included. Okay, you can unstage as well, and it tells you how to do that. So now let's commit. So again, I'm going to type in git commit, remember I need to include a commit message, so I'm going to use the same sort of style before. Remember the first time I made a commit, I was adding a brand new file. This time I'm going to use as my leftmost thing here the name of the file, and then I'm going to say what changes I made. So to my calc, I added a subtraction function. So that's a really clean, clear, concise way of saying the changes that were made on this this commit were that to my calc file, and I added a subtraction function. And those were the changes that I made. So somebody needs to go back and see what went wrong. They can see what I did was I added a subtraction function to that code. So I hit enter on that. You can see it says 1 file changed and 5 insertions. And let's have another look at the log now that we've made a second commit. So if I type in git log, we can now see we've got 2 entries to the log. We only had 1 before. And this is the latest entry. The latest entry always appears first. This is the head. And you can see that this is the changes I made now and where I added a subtraction function. So that's the commit message. And the previous time I committed was where I created that new file and added it to the repository. So now we've got a very clear log of the changes that I made, what I did, and by whom and when I did it. So I'm going to modify the code again because this is getting fun now, and I'm going to add a multiply function. But this time I'm going to introduce a sinister bug by accident, except it's slightly on purpose for the purposes of this. So let's add a multiply function here. Multiply numbers num1 and num2. And this time I'm going to accidentally, I'm not quite sure how I'd accidentally do this, but for the purposes of simplicity, let's just go with it. I'm going to accidentally add in an infinite loop. Oh no! But let's imagine I haven't noticed that. I must be particularly unobservant. So there we go, and then I'm going to have return result down here. Now, obviously, we can see that there's going to be a problem here, but we're going to imagine I haven't noticed that. So I've made those changes, and I've now saved those changes as well. So, what's that? Because I did introduce an error that I hadn't noticed. Right, so I've made those changes. I've got this bug in there that I haven't noticed, and let's go with it. Imagine I haven't noticed that. So I'm going to go ahead and I'm going to stage the file, and I'm going to commit those changes. Okay, so I'm going to go back to Git. Let's look at the Git status first. You can see it's picked up that I've modified it. So I'm going to add the changes. mycalc.py. So it's now been staged. If I check Git status, I can see it's been staged. And let's commit it. And I will commit it with the message in the same way as I did before, saying mycalc, and this time I've added a multiply function. Okay, brilliant. I'm very happy so far. I've added another thing. If I look at the Git status again, you can see the working tree is clean. Everything's been staged and committed. And if I look at the Git log again now, my log will look like this with the latest commit with being the addition of the multiply function. Okay. So the next day, let's imagine I go to run my fantastic new calculator program, and I'm horrified when I find myself using the multiply function, and I'm trapped in an infinite loop. And it brings back nasty memories of the last time I loaded up Vim. But it's okay, because I'm a good Git user. I don't panic. I think that's fine. This is why I'm using Git. So the first thing I do is I check to see what changes were made between the previous commit and the latest one, where the errors appeared. Remember, I can do that because I can look at the diff. The diff will track the changes made between commits. So to look at the difference, the diff between commits, I use the git diff command. Now, in order to do that, I need to specify the 2 commits that I want to compare by providing their identification numbers. Now, as I say, I can use the really long versions of those numbers, but in most cases, we can just use the first 7 digits. So to get that a little bit easier, I'm going to use the git log, but I'm going to use the 1-line option here, and that will automatically give me the 7-digit versions, which obviously are here, but this is a much easier to read way of doing things. So if I look at this here, I can see that the ones I want to compare are the latest one, the 721D32F here, which is where I did the multiply function, and this previous one here, the 6A9A25C one. I want to look at the difference between those two commits. So I'm going to use the git diff command to do this. So if I type git diff, and then I just simply give the two commit numbers. So 721D32F, you can copy and paste as well, 689A25C. I hit enter. Now this will show me the differences between those two functions. I've done that the wrong way around. Okay, so I want to do it the other way around with 6A9A25C, and the difference is then made as it went to 721D32F. There we go, it's better. So the order matters here, just to point out, that my error there was a good way of showing you that, that you're essentially saying, show me the differences from going from the first one to the second one. Okay, so in this case, I want to see the differences from going from this one, the 6A9 one, up to the one where I added the multiply function. So what this has done is it's returned the diff, and you can see that it's highlighted in green here, the additions that were made in that block of code. So the difference, the diff between those two commits was that this latest one added these lines of code here, which is what we expect, what we've just done. So I can now really easily see, I can see where the errors appeared. Now, obviously, it's very easy to see this in this very simple code. But imagine you've got a piece of code with thousands of lines and loads and hundreds of functions. It's not going to be so easy to work out where the problem is. So using a diff to see what was added when the problem occurred allows us to very easily be able to pick that up. So now we've picked up where the problem is, we need to revert it in some way. Now, there's lots of different ways to undo changes in Git, and that can make things a bit confusing. So Git is a wonderful piece of software, but it's also a bit complex and confusing sometimes with some of its stuff. And the way in which you undo things in Git is one of the principal ways in which it's a bit unfriendly. So here, we're going to use something known as a Git Revert. Now, what a Git Revert command will do is it will revert a specified commit back to the previous version. Okay. Now, this is considered what's known as a safe command because you don't lose any commit history by doing this. So the old commit with the bug you introduce will remain in that history, and we can go back to it if we need it. It'll basically just say, okay, I now want to add something new to my history, where I then went back in time and I grabbed I went back to the previous version. But everything is there. It's safe because we can undo that revert if we need to. So to call a Git revert, we need to specify the commit that we want to revert back. So in this case, we would specify the latest commit, i.e. the one that introduced the bug, the problem. And by giving it that commit, Git will then go back to the one before it. So that can be a little bit confusing at first. You might think, why don't you just say the one you want to go back to? What you're doing is you're specifying the commit that you want to roll back. So where in this case, it's the latest commit, and I want to go back to the previous one. So we give the latest commit as the identifier, and we give the git revert command. Again, we can use the log to let's just remind ourselves of the log. So I can use the log to grab the 7-digit identifiers. So remember, in this case, it's this one that we want to revert because that's the one that introduced the bug. Okay, and then I can just say git revert, and then I give that number. And by giving that number, it'll revert to this previous commit. So my code will go back to how it looked at this point. So if I type that in, now, because a revert is a type of commit, because you're essentially making a new commit that reverts, it will insist on a message. Now, you could specify a message at command line, but standard practice is that you just take the default for a revert. You take the default message that Git gives, and basically that's just revert and then whatever the name of the message that you gave for the one you're reverting. So revert my cult.multiply function means roll back that change, basically. So that's usually fine. So this is the point at which, if you're using Windows and you didn't change it, you will end up in Vim. Fortunately, I'm not in Vim here, and so I can exit quite easily. So however you want to exit your editor, so I just push Control and X on mine, and that will then accept that default message, and it will have made that commit. Now, if I look now again at the commit history of the Git log, I can now see that there's been a new commit which represents the revert that I've just done. So, and it even specifies here, this reverts commit, and then this number here. But all of the old stuff that I've done is still there. So where I added the bug, that's still in the history. So I can go back to it if I need to. But that's why it's a safe command that it's added this new commit as part of the history to say I've rolled back the changes that were made here. Okay. And you can see this as if by magic. If I now flip back to Spider, multiply function has magically disappeared. Now I haven't opened or closed or done anything in Spider. I've just had this file open the entire time, mycult.py, that single file. But because I've reverted the changes, and because this is being managed by Git and by the Git version control, because I've now reverted those changes, my working copy of this file in Spider has now gone back to how it was before I made those changes. And that speaks to one of the key benefits of Git and other version control systems, is that you only have a single file. I haven't had to go version 1, version 2 when I added the multiply function, version 3, etc. You just have a single file. As far as you're concerned, when you're in Spider, you're just using a single file, and you're just reverting that file and increasing the version, decreasing the version, and you're then working on whatever the current version of that is, according to how your version control system is working. And that makes things much simpler. Okay, so before we move on, it's time we talked about branches. So in Git, a branch refers to a line of development. And that basically refers to all of the changes in that development line and all of the history. Now, so far, we've just used the central branch, which is known at the moment as the master branch. Just a little note that this is soon going to be changed to be named as the main branch rather than master. So just bear that in mind if you're using Git in the future. And that means that all of the changes that we make are to the main code base. So we're just using the central master or main branch. Okay. But that's not really a very good way to work, even if it's just us doing the development. Because, for example, what we may end up doing is building in a new set of features, and we'll make a load of commits to add in these new features. And we're great, it's fantastic. I'm building all these new features into my program. And then I wake up one day and I'm not happy with this. This doesn't work in the way I expected. I don't think I like it after all. I think I want to get rid of all this development work and go back to how it was before I started on that line of development. The problem is, if we're just using the central branch, the master branch, we'd have changed that main code and we'd have to revert everything back. What would be better to do is every time we want to do some development, to create a new branch so that we branch off and then we make our changes, do our development work. And once we're certain we're happy with everything, we say, yeah, I want this now to be the features in my code. Then I can merge the changes back into the master branch. If I change my mind, or I find it doesn't work in the way I hoped it would, or it's too much of a hassle, then I haven't changed that master branch of development. And so I can easily go back and as though nothing had happened. So to create a branch in Git, we use the git branch command. The command names are very friendly. They're typically what you'd expect them to be. And we supply the name of the branch. So if I wanted to create a branch called dev as a development branch, then I'd use the command git branch dev. Now, what that will be initially is it will create a copy, an identical copy of the master branch, but it'll branch off. So any future work that I do in that branch will then be completely separate. But initially, it'll just take a copy of the master branch. But I can then play with that, safe in the knowledge I'm not changing the main code base. Now, if we use the command git branch without supplying a name, it'll give us a list of the current branches in the repository, and one of them will have an asterisk next to it, and that basically indicates the branch that we're currently in, the currently active branch. So just because we've created a new branch here, it won't automatically switch to it. We're still in the master branch. So we need to use the git switch command to switch over to the new branch. So let's do that now. Let's go back to Git. So first thing I'm going to do is create a new branch. So I'm going to say git branch dev. And if I type in git branch, I can see a list of the branches we've got. So I've got dev and master. You can see master is still the currently active branch. So I'm still in master. So if I want to switch over to dev, I say git switch dev, and I'm now in the dev branch. Okay, so now we've created and switched to a new branch. We can use this development branch to fix our buggy code. Okay, so at the moment, remember what we've done in the main branch is we reverted back before the bug. So we've now got a working version without that multiply function that introduced the bug in our main master branch. So the dev branch is identical at the moment to that master branch. So it's also got that the current copy is this here, where it hasn't been, we haven't added that multiply function. We've gone back in time, essentially. So let's access our history again. So if I go back to Git, type in Git Log. I should do that as one line. And I can see here that's exactly what's happened. So the latest commit on that particular branch for both cases is revert my calc multiply function. It's that revert commit that we made. Now, what we want to do in our development branch, now we're in our development branch, is to go back to that buggy code and fix it. Okay, that won't affect our main master branch. That's still safe with its working code, but without the multiply function. But what we want to do here is go back, reintroduce the, go back to the code that introduced the bug and fix it. And it's perfectly safe because we're doing this in the dev branch separate to the master branch. So if we look back to the one we want to go to, we want to go back to the one that added the multiply function where the error came. And so in this case, that's 71D32F. That's the one we want to go back to. This time, rather than using revert, we're going to use a git restore command. And a git restore command basically allows us to specify a commit, and it'll restore the content, the code content, from that commit as being the currently active code. Now that's different to a revert, which revert goes back to a previous version and commits and creates a new commit. So it says, okay, I'll roll back. This is now the commit. This is the working version of the code. Here with the restore, all we're doing is just saying, can you pull me in that code from that commit so that I'm working on that code. So we're not committing anything. We're just saying, grab me that code from that commit. So let's do exactly that. So to use the git restore command, I'm going to say git restore. I'm going to use this option called source. Now, source basically just indicates that you want to restore from a different commit rather than the current commit. Don't worry about that at this stage, just know that's what you have to type in. We also have to provide the Git ID that we want to restore the code from and the file name of the file or files that we want to restore. So I've only got one file, so it's just going to be mycalc.py. So if I go git restore, source, remember I want to grab the code from this one where the multiply function was added. That's the one I want to fix. So that's the code I want to grab back so I can make it a working piece of code. And then the file name, which is mycalc.py. Right. I've hit enter. Now remember, I'm in the dev branch. There's been no new commits. I've just told it to pull up that code. So if I go back to Spider, hey, it's magically back again. So this code has been pulled in. On the master branch, we've still got just these two functions here. But here, I pulled in that extra code. I haven't committed to this branch yet. I've just literally pulled that code back in so that I can fix it. Right, so now we've pulled the code in. I'm now going to fix that code. So we've got a working multiply function. Fortunately, this is pretty easy to fix. Let's get rid of that infinite loop. Put that over here, and I fixed it. That was a nice, easy fix. Fortunately, most fixes won't be quite that easy in reality. So once I've saved those changes, which I've just done, I can now stage and commit the changes. So at this point, I will create a commit. So if I go back to Git, so let's remember I'm still in the dev branch. Git add my conc. I check my Git status. I can see that's been modified and it's been staged, so it's ready for commit. And then I'm going to commit it, and I'll put in an appropriate commit message as well. And this time I'm going to use the keyword fix to indicate that I fixed something, and then I'll describe what I fixed. So I'll just say multiply numbers patched. So I fixed that function basically. Okay, I've committed that. So if I check out the Git status, I can see we're all working clean. Now I'm on branch dev this time, remember. So this has only been fixed in the dev branch, not in the main master branch. Okay, so let's have a look at the history. Just on that actually. But actually no, let's do that. So let's go back to the log. So if I type in Git log here. So if we look at the two latest entries here, we can see at this point, this is where we have the latest commit on master, and that's still the latest commit on master where we reverted back. But here, because we're in the dev branch, we've got, this is now our head where we fixed multiply numbers. And here's where it's deviated. So now we've got a different head on our dev branch to our master branch. There are differences. We fixed it in the dev branch. And we can see that if we were to switch back to the master branch, so if I say git switch master, so I'm now back on the master branch. If I now look at the Git log here, I can see the latest one is where I reverted. That fix does not exist here. So once we've tested the code that we fixed on the dev branch and we're happy that everything's working okay, we can add those changes back into the main code base, the master branch. And the way we do this is using something known as a merge. And the merge basically combines the changes from multiple branches. Now, you can merge two branches together, which is most common for smaller projects. The sort of things you're going to be doing typically will be just merging two branches. Or you can merge multiple branches, which gets a bit more complicated and is more common when you've got big, huge sort of multi-developer projects. The sort of stuff you'll be doing, you're looking at two branches really. So when you're doing a merge where you're combining changes from two branches, Git will look for a common base commit. So in our example, that's the head commit at the point at which we created the dev branch, because at that point, both branches are identical. Okay, so that's the common base. That's the point at which we split off. That's where they were both identical, and that's the common base. So once it's found that common base, it'll then create a new commit in the branch into which the changes are being merged, in this case, the master branch. We want to incorporate the changes back into master. That incorporates the changes from both branches' commit histories. Let's explain this with the aid of a diagram. So obviously in the example we've done, we've only made changes in the dev branch, but whilst we branched off in dev, there may have been changes made in master as well, okay? And we need to be able to merge these things back together. So here's what we mean by the merge. So we've got our master branch. We started off here. We just had a master branch. At this point, this is the point at which we split off and had created our dev branch. So we created a copy of this master branch that we could work on separately. So at that point, we've now got two development paths, the path on the master branch and the path on the dev branch. So this is the common base. And any changes from this point forward in each branch will be the ones that will need to be merged back together. So when we come to merge it back together, then it will combine all of the changes made in master to all of the changes made in dev from this common base. So in this diagram, that's the changes made in master over here and the changes made in dev in these two commits here. And it needs to combine all of that and merge it into one. So to perform a merge, in our example, we're going to merge the dev branch changes back into the master branch. And it'll be easy here because we've only made changes in dev. So we're going to switch. You first have to switch back into the branch into which you want to merge the changes. So typically that's your master branch. You want to switch into the branch into which you want the changes that you've done elsewhere to be brought back in. And then we're going to use the merge command to tell Git the name of the branch that we want to merge into. So I'm already in, I've already switched over to the master branch here. So all I need to do is say git merge dev. If I hit enter, then fast forward is the name of this, what I've just described, this way of merging. And you can see what it's done is it's merged the changes, which are a number of 5 insertions to the mycog file. So if we look at the history again in this master branch, we can now see here that I remember before when I looked at the history in the master branch, this was the latest, this was the head commit where we reverted. But now, because I've merged those changes, this is now the latest commit. And master and dev are back in sync once more. They've got the same head. It's where I fix the multiply numbers. Now in the main master branch, the main code base has had that fix applied. And if we go back to Spider in the master branch, we can see we've now got our multiply function, multiply numbers function is back as it should be. So you're probably thinking, sitting there, listening to me talking about merging two branches together, surely there's going to be a problem if you get a conflict. What happens if there's a conflict? And indeed, there can and will be conflicts. And in Git, this is known as a merge conflict. Now, there are 2 ways in which there can be a merge conflict. The first way is that the branches can't be merged because there are pending changes in the branch into which the changes are trying to be merged that could be overwritten by the changes we're trying to merge in. So, for example, in the master branch there, let's imagine before I did the merge, pulling in the changes I made in dev, merging that back into master. Imagine before that, I'd made some changes in master and I'd staged them, but I hadn't committed them. That's going to cause a problem because if the changes that I'm bringing back in, that I'm merging back in from dev, might overwrite that. So that's going to potentially cause a conflict. So in this situation, what Git will do is it will refuse to make the merge until what's known as the local state can be stabilized, i.e. the pending changes are committed. So you've then got a stable, clean working tree. The other way, and probably the more common way that you'll encounter, is that there's a conflict between the same lines of code. In other words, you've got a developer working on one branch and a developer working on the other branch, and they've changed the same line of code in different ways, or maybe one developer's removed a file entirely. So that therefore a conflict will occur if that happens, because the same code has been changed in different ways after the common base commit. Now there wasn't a conflict before, because all I did was I took I branched off with dev, I changed that code in the multiply function, and then I merged it back in. They might say, well, that's changing code because in the master branch, that code was different. And yes, it was, but I didn't change anything from the common base onwards. So because if I would have run into a conflict if when I'd gone into the master branch, when I started the dev branch, I'd gone in change the code, but then simultaneously over in the master branch, I'd also change the same code. Therefore, Git will have said, well, hang on, there are 2 lines of development here. You've changed one thing in one way and one thing in another way. And so I don't know how to sort that out. So in both cases, whenever it gets a merge conflict, the developer is the one that needs to resolve that conflict. Okay, so let's again go back to our picture to think about what's happening. So here is the point at which we split off the dev branch, leaving 2 development paths. So if changes were made to the same lines of code in these commits here as this commit here, but they were different changes and changes in different ways, we would get a conflict, and the conflict would happen when we try to merge back into master. Just to point out again, to highlight, there wouldn't be a conflict if, for example, C3D and C4D over here, these commits here, changed lines of code that were not changed over here. So if we did some development over here on the add function, and we did some development over here on the multiply function, that's fine. That's not a conflict. You just change different aspects of the code, but it's not the same code that's being changed. So I can simulate a merge conflict to see what happens in this situation. So I'm going to create a file called myconflict.py, and I'm going to save it in my repository folder. So I go back here, I'm going to create a new one. And I'm just going to create a simple function that just adds 2 numbers together. Bring it up from here, sorry. Okay, so I've just got it my function. I'm going to say result equals a plus b, and I'm going to return the result. Nice simple function. And I'm going to save that in my repository folder. I'm just going to call it my conflict to remember this is the one that's going to cause the issue. So if I call Git Status on this, we can now see here that it's picked up. Again, there's an untracked file. It's picked up as a file here that I'm not yet tracking called my conflict. So I'm going to now add that file. Add my conflict. And then I'll commit to the file as well. And I'll just have a commit message like I did before, indicating this is the first time this file has been uploaded. So init and then add myconflict.py. There we go. Okay, so I've now added that. Check out the Git status. It's all clean on the master branch. Now what I'm going to do is I'm going to switch out to my dev branch and I'm going to do some development. Remember, dev though is still stuck in the past. It hasn't updated with this new file that I've added because I did that in the master branch. So I'll switch over to the dev branch. I'll then merge master into dev so that I get the new latest copy, so that we're both working on the same common base. Okay, so I'm going to say git switch dev. Then I'm going to merge in master, git merge master. So now they'll have the same files, the same repository. So we'll have this new file in here as well. And I can show you that if I say git status. That one's completely clean as well. So now what I'm going to do, I'm now in the dev branch. I'm going to make a change to one of the lines of code. So if I go back to Spider, I'm going to change this to a minus function rather than a plus function. Okay, and I'll save that, and then I'll stage and commit those changes. I'll stage it first, and then I will commit. So I'm just going to put a commit message here. My conflict changed to subtract. Oh, change add to subtract operation. Okay, so that's the change I made. That's all good. That's all fine. No conflict so far. I've just opened up a new branch of development and I've changed a line of code. That's perfectly allowed. There's no issue with that at all. That's why you're doing it. But what I'm going to do now is I'm going to switch back to the master branch. Now, if I open up Spider in the master branch, of course, we haven't made those. We've made those changes where I changed this to a minus from a plus in the dev branch. So in the master branch, this is still plus. Okay, that's not an issue. As I say, that's not a conflict, except if I now in the master branch do this. Okay, I'm also going to change that line of code, but I'm going to change it to a multiply function. I save it. I go back to Git. I stage the file. And then I commit it. So I put in a similar message to I did before. Changed add to multiply operation. Okay. Now we've got the recipe for conflict. The conflict hasn't happened yet, because remember the conflict won't happen until we try to merge the changes. But I've changed the same line of code in different ways in the different branches. Let's now try, I'll go back into the master branch and I'll try merging the dev branch. So git switch master. Oh, what do we want master? So git merge dev. So before this was absolutely fine. Let's hit enter. And it's picked up there is a conflict, auto merging conflict. And it's picked up there's a merge conflict in my conflict.py and that the automatic merge has failed. It tells us to fix the conflicts and then commit the result. Remember, it goes back onto the developer. Git can't fix this for you. You need to do it as the developer because it can't make that decision about what should work and what shouldn't. So we need a bit more information to try and work out what we're going to need to do here. So let's first call the Git Status command. And this tells us that we, on the unmerged pass, that both have modified this myconflict.py file. So this tells us that this is the file where this has happened. Remember, obviously, we know that because we're just doing this one file. But in a large project, that may not be apparent. So we know that the problem is that both branches have modified myconflict.py in some sort of way that it can't be automatically resolved. But we're still going to need a bit more information. Let's flip back to Spider. What's happened here? We've got some weird symbols that have appeared in our code. Now, this is what Git has done for us to try and help us work this out. So what's happened here, flip back to the slide for this moment. So the equal symbols that are here indicate the center of the conflict. Okay, so Git has said, this is the center of the conflict. Everything between that and the less than arrows above, so everything between this and this is the content that's in the head of the branch that we're currently in. So in this case, the master branch. So this is what master has done. Remember, in master, we change it to multiply. Everything between the center and the greater than symbols here is the stuff that's in the head of the branch that we're trying to merge into this one. In other words, the dev branch. Remember, that's where we made the change it into a subtract function. So what this is doing is it's telling us this is the center of the conflict. Everything up here is what you're trying to say this code should be in the current branch. And everything down here is everything the developer for the other branch has said should be for this same line of code. So now we know where the conflict lies, we can work out what we need to do. And we basically have to make the decision about how to fix it. So in this case, we need to decide, well, do we want it as a multiply function or do we want it as a subtract function? We've got to make that decision. Or do we combine them both in some way? But we can't leave it as it is. It won't work. So I'm going to fix, I'm going to assume this time, yeah, actually, let's forget about the minus function. Let's just make it a multiply function. So I will remove this subtract thing. I also need to remove these little symbols that Git has added, otherwise the code won't work. So I'll take that out and I'll save that. Now, so basically what I'm doing by doing this, because the merge failed as a conflict, we're in something known as merge mode in Git. And basically this means that whilst we're in merge mode, we can't do things like switching between different branches. Git is waiting for us to fix this problem. We have to fix it in some way. So when I make these changes here, and then I stage and commit them, I'm basically declaring this is how the merge code should look. Forget about that minus thing. this is how I want it to look. This is how I want you to resolve it. It should look like this. Okay. So I will do that. I will add, go back to Git. I will stage the changes. And then if I look at Git Status, it'll say I'm on branch master. All the conflicts are fixed. It's picked up. That's okay. What I've done is enough to fix the conflict. But I'm still merging. I'm still in merge mode. I still need to formally commit this to resolve the conflict and to conclude the merge, because I'm still in that merge mode. So I will type Git Commit to make that commitment, and I will add a little message here: fix resolved. I say merge conflict in my function of my conflict.py. I enter now. It's identified that the fix has been resolved, and the conflict's been resolved, and there has been fix, and that's fantastic. And then if I type Git Log, we can see at the top here that this has now been fixed. That latest commit has merged the things back in, and it's fixed it, and that's resolved the conflict. But you will notice one difference is that dev isn't now listed within this thing here under the head, and that's because dev is still stuck with the subtract code. So we fixed it to merge it back in to the master, but dev's still got the minus code in there. And we should bear that in mind if we were going to do any more development in the dev branch, that we'll need to resolve that in some way, probably by merging master back into dev, so that we're working on the newest copy again. Just a couple last things before we finish. So .git ignore is a really useful way in which we can specify Git to ignore certain files. So when we're on a real coding project, it's likely you're going to have lots of coding files, and you may want to commit and stage lots of files at the same time. You're not just going to be doing it sort of file at a time as we are here. But there's also likely to be files that you don't ever want to include in your repository. For example, you might have results files that are generated by your model. You almost inevitably will. Well, they're going to change every time you run the code. You don't want to have to track all those changes and be bloated. There's no need to do that. You know, there's no benefit. It's not going to tell you anything. Or it might be that we've got raw data files that we're using that might contain, you know, patient information, for example. We don't want to upload those to our repository. So if there's files that we want Git to ignore, we can create a .git ignore file, which basically provides details of all the file types and or directories we want Git to ignore. And we just create a new file, a simple text file that has the name .git ignore. And then we list the files and file types and directories that we want Git to ignore. So before, whenever we put in a new file, it was saying, oh, I'm not tracking this, but you know there's a file over here that I'm not doing anything about. So if you put those file types in a .git ignore, then it will completely ignore them, and it won't do anything and say, okay, I know you don't want me to pay any attention to that whatsoever. And you also have to stage and commit the .git ignore file as well. Now, because this is a type of file that's preceded by a full stop, this indicates to your operating system that it's a hidden file, which means that if you want to be able to see it or access it from your graphical user interface, you would need to select the option to view hidden files or directories in your OS. Usually, it's on Linux, you can just hit Control and H, and it will show those files. I can't remember if that works for Windows or not, but there is an option that allows you to see them. So .git ignore file might look something like this. We can use comments in the same way as we do for Python files. And I can say, for example, here, that will tell Git to ignore any files with the file name .log. It'll tell it to ignore this specific file here, results.csv, and also to ignore anything in the results folder. And there's a little link here that you can read more about the patterns that you can use in a .git ignore file. And the last thing just to mention is the readme.md file. This is another type of file that's good practice to have in your repository. Basically, it's just a way to create a README file for your repository that explains what your project is, how it works, etc., etc. This is really important, not just for other people, but for yourself. Remember, believe me, you will forget how to do things and how parts of your own code are working. That will happen. So having a README file which documents how the program works, gives an overview, and how you should run it, etc., is really important. So it's worth always including that as well. And also, if you upload it to, you're going to go further and upload your Git repository to GitHub, then a readme.md file will automatically be designated as the documentation for your project. So I've only gone through most of the basics, a bit of a whistle-stop tour of GitHub. Apologies that it's gone a little long. I was going to get you to practice this. So I'm going to talk to you in a second just about what I want you to do. If you find some time over the course, I'd encourage you to have a go playing with Git yourselves. You might want to have a go as a group as well, and come together as a little group, or just do it by yourselves. But I have just gone over the basics of it. There's much more that you can do, much more to learn about Git. Here are some links. Here's the link to Tom's excellent materials, which this training is based on. There's fantastic, a really well-written tutorial here by Software Carpentry that will take you through the basics and also goes into details about collaborative version control and licensing options for your code, which is really important if you're thinking about using making your code free and open source. Thinking about how you license it. You'll notice that the HSMA materials are licensed under a free and open source license, and there are lots of different ones, and you can choose different things depending on how you want to license your work. There's this fantastic website here, OSH*T Git. You will need to replace the asterisk there with a letter. I'm sure you can probably work out what that letter is supposed to be. It rhymes, if that helps. And it's probably also the thing that you will say the most when you're using Git, because Git is a bit of a pain to use sometimes, and you will get into a mess with it. But fortunately, this little website will tell you what to do when something's gone wrong and you've gotten into a mess, and it'll tell you how to get out of it. And then finally here, there's a little tutorial that takes you through from the basics of Git, and then all the way up to using GitHub with your newly created repository. So as I say, we haven't had time to do the exercise today, so apologies for that. But do make sure you have a little look at that. It'll basically take you through doing something very similar to what I've just done here, where you'll try, creating new files, modifying them, staging, committing files, and also creating a conflict and seeing how you would resolve that. So do have a go at that to practice using Git, because it's a good skill to have, and it's a good skill to have right from the off in your development journeys. Okay. Any questions about anything that I've covered on Git before we close off? Probably bored you all to sleep, I'm sure, by my relentless talking about Git. Obviously, if you do have any questions about Git, do post them in Slack, and we'll be happy to help. But do have a practice at using it, and it's, as a good practice to get right from the off into using Git for your projects. So hopefully this morning has given you a bit of an overview about why free and open source development is important, why you should be adopting this for the kind of work you'll be doing, and to give you an excellent version control system that you can use to help both you and others in terms of your free and open source collaborative development. So I look forward to seeing you all on Tuesday when we will have the SymPy session. So we will start showing you how to build models in Python. So by the end of Tuesday, you're going to be able to build a discrete event simulation model, which I think is quite exciting. And I hope you're excited about that too. So until then, I look forward to seeing you then. If you have any questions in the meantime, please let us know. Otherwise, see you on Tuesday. Do make sure you've got the materials downloaded and ready. Please make sure that you've installed SymPy if you haven't already using the instructions. You probably all have done that anyway, because I advise you to do that when you first installed the software as a sort of test, because you're going to need SymPy using pip install SymPy. But if you haven't, do make sure you do that, because you will need to start using SymPy on Tuesday. Fantastic. See you all then. Hope you've had fun and have a nice weekend, everyone. Goodbye.